In this lesson, I'll show you how to solve a potential energy spring compression problem. This two-part question reads, place a 3 kilogram block at the top of a 3.4 meter high frictionless incline. At the bottom of the incline, the block encounters a spring with a constant of 400 newtons per meter on a horizontal surface. In question A, if no energy is lost to friction, how far is the spring compressed? And later we'll answer, if the horizontal surface has a coefficient of friction of 0.20, how far does the block slide while compressing the spring? With that being said, let's begin by making an illustration of what's happening. Let's say our mass is on this inclined plane, and our mass is represented by this rectangle. The height here is 3.4 meters, and there's a spring at the very end that has a constant that's equal to 400 newtons per meter. Given that this mass is at a height that is 3.4 meters, it has potential energy, and that's due to three things. The fact that it has mass, there's gravity, and this height. And because of that, potential energy is calculated using the formula mass times gravity, and that's the acceleration due to gravity, times the height. So let's begin by calculating the potential energy, because since this is a frictionless surface, the energy that it holds up here is equal to the amount of energy that it is down here. So we can use this value as the amount of work needed to compress this spring once this mass has reached this point of the plane. If that's confusing to you, let's begin with this first step by calculating the potential energy. So the mass is 3 kilograms. The acceleration due to gravity is 9.8 meters per second squared. And the height happens to be 3.4 meters. From here, we'll use our calculator to find out what that is equal to. And as you can see, it is 99.96. 99.96 joules. Joules is the same thing as newtons times meters. And newtons is kilograms times meters per second squared. So it makes sense that rather than using all of this, joules is a better replacement. It's simpler and cleaner. So that is the amount of energy that this block will have at the very bottom. And this work will be used to compress this spring. In one of our previous lessons, we learned that when it comes to springs, force is applied linearly, and that's the usual case. And the work required to compress a spring when force is applied linearly is calculated using the formula W is equal to K as the constant times x to the power of 2 over 2. The work that will go into compressing this spring we found is 99.96. So I'll replace W with 99.96, and that's equal to our constant K, which was provided in the question. Don't forget to write down the units along the way. So 400 newtons per 1 meter times x to the power of 2 over 2. By solving for x, we have solved question A, the distance. So let's solve for this x. I'll multiply both sides by 2, and that gets rid of this 2, and now it's over here. And divide both sides by 400. So if I divide this side by 400, that and that cancel out. And by calculating this, we are one step closer. So 2 times 99.96 divided by 400 makes this number 0.4998. 0.4998 is equal to x squared. We square root both sides to get rid of that squared value. We get 0.7069. Now, to the correct number of significant figures, we should only have two significant digits. So 0.71 is the correct representation, and the units are in meters. Now, of course, when you square root a value, you get a negative, right? You get negative 0.71 and positive 0.71. We're going to ignore the negative version because it doesn't make sense in this question. In part B, if the horizontal surface has a coefficient of friction of 0.20, how far does the block slide while compressing the spring? Obviously, it's going to be less than 0.71 because the potential energy is going into compressing the spring and it's going into overcoming the friction. So just be mindful of that. We will write down part B. Remember, the potential energy we calculated was 99.96, and that's going to equal to the amount of work required to compress the spring, that's represented by this expression, plus the amount of work required to overcome the friction. Here's how we represent that. W is equal to the coefficient of friction, which we represent as the letter mu, times mass, times the acceleration due to gravity, times x. Remember, the variable x represents the displacement. Work is always calculated by taking the force times the displacement. So I'll add that expression, the one that we just wrote, where I will replace these values with what they actually are. So 0.20, the mass was 3 kilograms. What else do we have? The gravity is 9.8 x. We have an equation that is a quadratic, x to the power of 2. So we might have to use the quadratic formula to help us solve this. Let's simplify. 99.96 is equal to 200x squared. Let's multiply these using our calculator. 0.2 times 3 times 9.8. That's equal to plus 588x. Solving for x, we need to bring that constant over. So we have 0 is equal to 200x squared plus 5.88x minus 99.96. Now I'm assuming you know how to use the quadratic formula, so I'll skip ahead and just use a function on my calculator that will enable me to find x really quickly. So I'll put 200, 5.88 minus 99.96 as A, B, and C. And we get two values, 0.69 and negative 0.72. We will ignore the negative version and just keep the positive version as 0.69. So as you can tell, when there is friction, the distance that the spring is pushed is less, because now you have to overcome that as well. The units for this are in meters, and that concludes our video on potential energy and spring compression.